This is Jack Jackson. We're going to look at taxicab geometry today. Just a little brief introduction to the geometry and to some of the tools that we can use with that that I've developed for Geometry Sketchpad. So taxicab geometry is a geometry very much like Euclidean geometry in many ways. The points, lines, planes, line segments, and even angles are defined exactly as they are in Euclidean geometry, and even angles are measured in the same way as Euclidean geometry. So we can use all the standard built-in tools for making all these tools here, these straight edge tools for making line segments, rays, and angles. We can use the point tool for making points. We can use our transformation tools for rotating things to work with angles exactly like we would in Euclidean geometry. However, the big difference in taxicab geometry and Euclidean geometry is the distance metric. It's how we measure distance. So in distance, when we measure distance, basically we can think of a coordinate plane here, same as we would a standard Cartesian coordinate plane in Euclidean geometry. So down here we have an x-axis, okay, and it has, let's see here, let me move this up just a little bit. We have an x-axis, and a y-axis, okay. And so I think I have this thing set on snap points at the moment, so it's going to have integer coordinates. So what you want to think of in taxicab geometry is measuring distance as you would have to go, say if you were driving a taxi in a city, say a city with north-south avenues and east-west streets. And so here we would go 1, 2, 3, 4 blocks to the east and 2 blocks north. So we have to go a total of 6 blocks to get there. Now if we could fly, we could go like Superman or something. We could fly right through buildings or whatever. We could go a straight distance here, and we would go this way, and that would be how we would measure things in Euclidean geometry. Okay? And of course Euclidean geometry, the distance metric is determined by the Pythagorean Theorem. Notice we have a right triangle here. So we take this distance here, which is absolute value of delta x. This one is absolute value of delta y. Take delta x squared, delta y squared, add them up and square root. That's our distance in Euclidean geometry. But our distance in taxicab geometry is given by taking the absolute value of delta x and absolute value of delta y and just simply adding them up. Now we're going to do this even if we go up here and turn off snap points. And now we're going to think of the length of this line. So this is still going to be a line segment, but we don't necessarily. Now we sort of remove all the buildings and everything from our plane, and we're still going from here to here, but we just measure distance the way we measure like this. So you can still think of going along this path, okay, but you measure distance as we would in this city manner, okay, and so that gives us our basic distance. Now, one of the things that we want to do is we want to have a tool to measure distance. Well, we have a tool to measure distance up here for Euclidean distance. Now, one thing I want to warn you about is this. The tool that I've got defined here uses this coordinate grid, assumes the coordinate grid is there. If you go in and just create a coordinate grid, it normally has a control point here, which I've hidden, that allows you to change the scale. When you do that, the distance measured in taxicab geometry is going to be based on that scale, whereas the distance you measure from Euclidean up here is going to be measured not on the coordinate system, but rather on just some scale that it's got built in. So when you change the coordinate system, it does not change the distance in Euclidean, but it does in taxicab. So it's going to be very important that you use a scale where distance from 0 to 1 here is 1 centimeter, and you don't change that. So you want to hide that point so nobody can, including you, doesn't accidentally change that scale on the coordinate grid. Now with that said, we've got a tool here called t distance, and what you do is you just click on 2 points and it gives you the t distance, and it's actually based on whatever these 2 points are named. Right now they're named L and M, but for example I can name them D and E, and notice that it has a text here that says DE Taxicab is 4.42 whatever, and it also refers to it here. So we can use this in doing further calculations. We can do this. We can hide either one of these if we want. And so we have the distance between the 2 points, or in other words, the length of that line segment. And that's how the tool works. So you can click on 2 existing points, or you can make 2 new points. Pretty simple tool, pretty easy to make, but important that you understand that it is based on this coordinate system. Now, next thing we want to do is talk about a circle. Now remember, a Euclidean circle is like this, and it's the set of all points in a plane so that the distance that are a fixed distance from the center point, the length of this fixed distance is called the radius of the circle. That's called a radial segment. Okay, and so that stays the same distance as we move this around. Okay, now what we want to do is we want to make the same kind of object, the same definition. We want to make it in Taxicab, a Taxicab circle. Well, what would that be? Well, let's start by thinking about it here. If we start here, and let's say we want to find a distance, all the points at distance 1. Well, the grid lines are 1 apart, so if we go, let me just go to, we'll just go here, we'll go to snap points. So these points are a distance of 1 because a Euclidean distance and Taxicab distance are the same. So now remember, once again, a Euclidean circle through these points would go like this. So that's a Euclidean circle, but not necessarily a Taxicab circle. Okay, so what would a Taxicab circle look like? Well, let's think about it. Certainly it wouldn't include some of these points here because we know anytime you're at a slanted distance here, let's take a line segment here like this. Okay, and we want to find the length of that line segment. Well, if you are, let's turn off the snap points now. Straight out here, it's going to be the same distance as the Euclidean distances of 1. But if you go out this far, you've gone out a Taxicab distance more than 1, because we know these 2 legs of the triangle that we're adding up turn out to be more than 1. So where would we be? If we back up just a little bit, let's say we back up a half a unit here, then where do we need to go? How much far up do we need to go to still be a distance of 1? Well, if this is half a unit, then we need to go half a unit up. Okay? So, however far we go here, we go up the same distance here. Or if we go 3/4 of a unit this way, then we're lacking a 1/4 of a unit, so we need to go up a 1/4 of a unit. Well, what kind of shape is this going to generate for us? Well, I'll show you. Turns out to be a circle in Taxicab. Turns out to be, let's make it radius 1 here. Here's our circle right here. Again, I'll put it on the grid line. And notice what happens here is when we go somewhere, let's just put that here, anywhere on this circle, which is a Euclidean square, oriented in such a way that the diagonals of the square are parallel to the coordinate axes. Okay, that's one way to say it. Or the sides are sloped with a slope of 1 or negative 1. 1 or negative 1 for the slope of the sides. But this goes around like this. Now, why would it be like this? Well, think about it a minute. However far you're going across here, the part that you're lacking for the distance, so the distance one way is A, and the other one is 1 minus a. Okay? So suppose we take this and just place this at the origin. Okay? And it doesn't have to be a distance of 1. It could be any distance. Let's say 2. Okay? And so anywhere, so for example, right 1 up 1, right 1 1/2 up 1/2. Okay, why would it be on a slope? Can we prove that it's on a slope -1 between these 2 points here and here? Certainly it's easy to see that these points at where the x or y coordinates are 0, that the other coordinate is going to have absolute value, the radius. Okay. So let's go over here, for example. Okay, what would the coordinates of this point? We want to show that if it's on this line, that it has those same coordinates. Okay. So maybe we can actually go write this down here. Okay. So we're looking at something like this. This is the origin. This is the point. Well, whatever the radius is, r0. This is 0, r, negative 0, negative r, 0. So those are the vertices of our circle. So a circle is a quadrilateral here, made up of 4 line segments. Okay. Now we want to prove that if we take a point here or here, let's say we take one here, coordinates are x, y. What's it going to be for that to be the distance? Well, we're looking at this right here. Now, it's centered at the origin, so that's the distance from 0. Well, the distance from 0 is going to be absolute value of x plus absolute value of y. Is going to be the distance, and that's supposed to be whatever the radius is. So let's go ahead and solve for y. That's absolute value of y equals negative absolute value of x plus r, or in other words, r minus absolute value of x. Now, what are the possibilities here? There's actually 4 of them. If y and x are both positive, first quadrant, this is just y equals r minus x. And that's going to be the equation for that one right there, that side. If x is positive, let's see, we'll do second quadrant next. Second quadrant is when x is negative and y is positive. Well, y is positive, the absolute value of y is y. And if x is negative, the absolute value of x is the opposite of x, so this becomes r plus x. So this is y equals r plus x is the equation for that side. Okay, what would the equation for this side down here in the third quadrant be? Well, let's see here. Remember the absolute value of a, is a if a is positive or 0, and it's the opposite of a if a is negative. We're using that piecewise defined definition of absolute value here. So in this quadrant, both y and x are negative, so we get negatives both places. Okay, so we could get y. So when we finally solve for y, we're going to divide by negative, so it's negative r. Okay, so negative on x makes that positive. The minus is going to make this negative. So this is y equals negative r minus x. And finally, this side here is x is positive, y is negative, so it's y equals negative r plus x. And so, sure enough, what do you see? You see that is exactly what are these. So we solved these equations without actually looking at this. We just looked at an arbitrary point, x, y. And what does that turn out to be? Each of those turns out to be a line okay, in Euclidean geometry, and of course also in Taxicab geometry. And so of course it's only going to apply for certain values, right? And so this is when y is negative, x is positive, and so forth. So it's only a line segment, and so we get these 4 line segments, and you notice they all have slope 1 or negative 1. So whenever we look at the diagonal, so the diagonals go like this. Notice, of course, they're perpendicular to each other, but well, in this case, they're actually on the coordinate axes. So that shows you that that we do have this idea of taxicab circles. So now that we know what they look like, we need a tool for making them. Now, unfortunately, what we came up with a formula for each one of these was 4 different pieces. And luckily, since we know what they are, it's not too difficult to come up with a tool to come up with these 4 points here. Pretty easy. So let's say we want to do a tool by radius, a circle by radius and a point. So we know radius and center. So remember, when we have taxicab circles, what can we do? Euclidean circles. We construct a circle by center and point, or by center and radius. And so we want those 2 tools in taxicab geometry. Okay, so what does that give? How are we going to do that? Well, if we look here, what we want to do is take a point. It's easy to come up with these 4 vertices. All we have to do is say, if we do this by a parameter giving us the radius. So we have a distance parameter 2, and this says we go to the right and left 2, and up and down 2. Okay, and then we can construct it in Euclidean in Sketchpad very easily by just constructing these line segments. Okay, the problem with that is you can't do what I'm doing right here, which is make one point go all the way around the figure. Okay, there is a way to sort of make it jump around and go around the figure here, but it's a little bit problematic. Okay, and these 4 sides are 4 different objects as far as Sketchpad goes, which is why you can't really make the same point really go all the way around. So that's a little problematic. So one way we can get around that is by doing a parametric equation. So down here we see a parametric equation. So what we want to do is look at this parametric equation. So if we take a center AB and a radius capital R, it turns out that these parametric equations work. We let x be r times cosine of t plus a. So if you think about this, it's just like you would parameterize a circle that you may have done, say, in your Cal 2 or Cal 3 class, or maybe even in a pre-calculus class, like a trigonometry class you might have done this. So we can think of t as essentially being the angle, theta, and it's going to go from 0 to 2 pi. And we want x to be r cosine of t would give you a circle centered at the origin. We shift it over by a will give us a circle centered at a. Then we want, if we wanted Euclidean, so this is going to give us the x's of all the points that we'd normally have on a circle of a Euclidean circle like this. Okay, which of course we want the same x's on this circle. But if we were wanting Euclidean circle, the parameter would be r sine of t plus b would be what we'd need for the points on the Euclidean circle for the y's. But we have a different one here, and we're going to use this here. Okay, and this formula right here works out to be the correct one. So I'm going to leave it to you as an exercise to go through and see if you can make sense of this formula here, y for a particular x going from here all the way back. When it's based on the angle t, we can figure out why it would turn out to be this. Now, we are using a sine and cosine function here, okay? So it's very important when we're doing this that we're doing things in radians. So when you go here to Edit, Preferences, you want to make sure your angles are in radians anytime you use this tool. So when you're working with pretty much anything in my college geometry class, with a few exceptions that will be clearly given, we're going to want our measurements to be made in radians. In particular, anytime we use this tool here, we want it to be in radians, so that this will turn out to go all the way around. Okay, and this gives us our circle. Okay, and so that gives us a circle that we can do by parameters. So we can set up a distance measurement, either something we've measured somewhere else, like this distance measurement, okay, or a parameter. So we can make a parameter this way, so number, new parameter. Then we're going to make this a distance measurement, because this was made based on a distance, by just translating, well, and using this. So let's see here, radius 1, and we'll give it a number, say radius of 3. Okay, and then the way our tool works is you go down here, it's by center and radius, so center, and then you click on the radius, and there's your circle, and it's controlled by this parameter. So if I make it a radius 5, there we go, or radius 1, so there's a unit circle centered at wherever we want to center it. Okay, so that's by center and radius. Once we have that tool, then we can make one by 2 points, because what do? We just take 2 points, we measure their taxicab distance, here we go, and then we build a circle based on that distance, right? So now we use the tool that says center and radius. We pick one of these to be the center and click the radius, and now we have it, but notice it's based on this point here, which we can move around the circle, taxicab circle, and move it anywhere we want. So now we have a circle that's based on those 2 points. Then we use that to generate a new tool, and that's the tool here that says by center and point, like this. Now, thought I had another tool. Okay, well, I'm going to make another tool. Now, the only problem with this is whenever I would like to be able to find the intersections of circles. So I'd like to be able to take this and construct an intersection, but notice it will not let me do that. And the problem is that Geometry Sketchpad will not let you find the intersection points of 2 parametric curves, which is what we really have defined these as. So that's not so good. So maybe what we want to do now is we want a tool with something like this, maybe by center and a circle by center and radius, okay, but we would like to define those additional, we'd like to have the additional sides here where they're individual sides. Then we can talk about those individual sides. Those are objects which can be intersected. Okay, so if I have, let me just make a copy and paste. So we have this. Now the only problem with using this is there are many different points of intersection that we might have to generate. So notice we've lost some intersection points. So we have to kind of go through here and identify all the different points of intersection. Well, if we do that with a little bit of work, we can actually eventually get all the possible intersection points and identify all of them. Okay, but it takes a little while to get them all identified. But with that, you can do intersection points. So it's useful to sometimes make the sides then whenever you want to go ahead and make those those points able to find intersection points. So not a perfect tool, but pretty useful for what we need. So now we have tools for these things that are very similar to our Euclidean tools, and we can use them in a very similar manner to explore lots of good topics in Taxicab's geometry.